Okay, so let's start for today. So today we'll discuss the assignment 8 for the course Linear Algebra, NOC 23 MA 03. So let me start the script. Hello? Yeah. So first question is n cross n matrix A is given over R and it is called nilpotent if a to the power k is 0 for some k, and the matrix is called idempotent if a square equals to A. Then you have to check which of the following statements are true. The first option is any nilpotent matrix, all nilpotent matrices are diagonalizable. Right. So let's check. So the first option, nilpotent means, so A is nilpotent if a to the power k equals to 0 for some k belongs to n, right? And A is nilpotent, idempotent. So this is 1, and A is idempotent if A square equals to A, right? So the first option is saying that all nilpotent n cross matrices are diagonalizable, right? So let's take one example of nilpotent matrix. Take A equals to this 0 1 0 0. Then A is a nilpotent, right? So let's square it. What it will become? A square 0 1 0 0 0 1 0 0. So it's 0 0 0 0 here. It's again 0 0. So A square is a 0 matrix, right? Which implies, so A is a nilpotent matrix. Right. Now is A diagonalizable, right? So we have to check that A is diagonalizable or not. So let's check this. So let's find the characteristic polynomial of A. So what is the claim? We will show that A is not diagonalizable. Claim, we will show A is not diagonalizable. Right. So let's find the determinant of A minus lambda I. What is this? Determinant of is minus lambda 1 0 minus lambda. So determinant is lambda square. So characteristic polynomial is lambda square. So what are the eigenvalues? So only eigenvalue is 0, right? So det A minus lambda I equals to 0 imply lambda square is 0, which implies lambda equals to 0 is the eigenvalue, the only eigenvalue, right? So now, so we get one eigenvalue. Now let's check what is the corresponding eigenspace of 0, E0, right? So we have to find the eigenspace. So let's find T of B. Let's B be the eigenvalue, eigenvector corresponding to the eigenvalue 0, which imply, or 0 1 0 0. Suppose take this is xy, then it will become 0 0, right? So what you will get? So you will get y, and this is 0 equals to 0 0. So which implies y equals to 0, right? So the corresponding so the eigenspace corresponding to the eigenvalue 0 corresponding to the eigenvalue 0 is, which denoted by E0, is the all such vector B such that TV equals to 0 times B, right? So this contains, so if xy is a vector in E0, then the y second component should be 0, means it contains all the points x comma 0, right, or x in R. So this is the eigenspace. So note that this is one dimensional, right, because x comma 0. So note dimension of E0 is 1, right? So the eigenspace corresponding to the eigenvalue is E0 is one dimensional. So it has only one basis. So let E0 is the span of V, right? But T is a map from R2 to R2. But the corresponding linear operator T of A or L of A you can denote. But L of A is a map from R2 to R2, right? So this LA do not have the basis in eigenbasis or the corresponding. So you can write that LA let's write LA is from R2 to R2, right? And we get only one eigenvectors, right? Which implies LA or R2 do not have basis consisting of eigenvectors of LA. So right, so if the operator is diagonalizable, then the V should have a basis consisting of eigenvectors of the operator, right? But here we see that R2 do not have a basis consisting of eigenvectors of LA, which implies that LA is not diagonalizable, means the corresponding matrix is not diagonalizable. A is not diagonalizable. So you have seen that this matrix is nilpotent but not diagonalizable. So the first option is false. All nilpotent matrices are not diagonalizable. Right. So come to the next option. What is saying? There exists exactly one nilpotent n cross n matrix such that A is diagonalizable. Right. So we will prove this that this is true, means the only nilpotent matrix which is diagonalizable is the 0 matrix. So let's prove this. So this is option number 2. So what we will prove? We will prove that the only nilpotent matrix which is diagonalizable is zero matrix. Right. So let take A be an nilpotent matrix. Let A be a nilpotent matrix. Means there is some k such that a to the power k is 0, which implies a to the power k is 0 for some k belongs to natural number. And suppose, so we will prove this by contradiction. Suppose let's assume that A is also diagonalizable. So also assume that, and we prove that A will be zero matrix. So also assume A is diagonalizable. So A is diagonalizable means there exists a invertible matrix, which implies there exists a Q which is invertible matrix such that A can be written as Q D Q inverse, or D is the diagonal matrix. D is diagonal matrix. Right. Now take the kth power both sides, means so what will happen, this Q D Q inverse, if you take the kth power, so you can check that simply the Q inverse, they will cancel up if you just square it. So let's, what will take when you square it, a square means Q D Q inverse and Q D Q inverse, right? So by associativity Q inverse will cancel, so you will get Q D square Q inverse, right? So by induction you can prove that a to the power k will be, so therefore a to the power k will be Q D to the power k Q inverse, right? And A is also nilpotent, it's given, means a to the power k is 0, so 0 equals to a to the power k equals to Q D to the power k Q inverse. So we get d to the Q D to the power k Q inverse is 0, so which means d to the power k is 0, right? Because Q is invertible. We can take multiply both Q and Q inverse from both sides, so we get d to the power k is 0. But note that D is diagonal matrix. But note D is diagonal matrix. And its kth power is 0 means D should be 0 matrix, right? So d to the power k equals to 0 implies D will be 0. Means the entries are kth power is 0. So if it is the entry is non-zero, its kth power is non-zero, then the entry should be non-zero, right? So the diagonal matrix itself is 0, and if D is 0, because A is QD Q inverse, so which implies A, which is QD Q inverse, so it's 0 matrix. So we get A is the 0 matrix. So we start with the assumption that A is diagonalizable and both nilpotent, and we get A is the 0 matrix. So we have shown that the only nilpotent matrix which is diagonalizable is the 0 matrix. So the option is correct. There exists exactly one nilpotent matrix which is diagonalizable. So option number 2 is correct. Let's take the option 3. if A is in M2R has trace 0 and determinant 1, then A is diagonalizable. Given that it's 2 cross 2 matrix, trace is 0 and determinant is 1, then you have to check that it is diagonalizable or not. So option number 3, A belongs to M2 of R, trace of A is 0 and determinant of A is 1. We have to check that A is diagonalizable or not. So let's take this matrix. Take A equals to 0, 1, minus 1, 0. Right. Note that all the diagonal entries are 0, means trace is 0. So trace of A is 0. And what is the determinant? It's 1. Determinant of A is also 1, right? But is this matrix diagonalizable? So let's check that is this diagonalizable or not. So compute the characteristic polynomial first. As we will show, this is not diagonalizable. We saw that A is not diagonalizable. This we have done in the last class, that A do not have any real eigenvalues, right? So from there it will follow that A is not diagonalizable. So let's check again. So what is this? Determinant of A minus lambda I. So this is determinant of minus lambda 1 minus 1 minus lambda. So lambda square plus 1. So its characteristic polynomial is lambda square plus 1. So you can see that it do not have any real root. So which implies that this matrix A do not have any real eigenvalues. Therefore or note that so lambda square or so A do not have any real eigenvalues. A do not have any real eigenvalues, which means A is not diagonalizable. Right. So option number 3 is false. Let's check the option number 4. A is idempotent matrix. If A is idempotent matrix, then both 0 and 1 are the eigenvalues of A. So idempotent means A square equals to A. Then you have to check that both 0 and 1 are the eigenvalues or not. So this is option number 4. Given that A is idempotent, given A equals to A square means A is idempotent, right? So we have to check that both 0 and 1 are eigenvalues or not. So let's take A equals to identity matrix. Take A equals to I, identity matrix, 2 cross 2, 1 0 0 1. So note that this is idempotent, right? Note I square equals to I, right? Which implies I is idempotent. But what are the eigenvalues of identity matrix? This has only 1 as eigenvalue, right? 0 is not the eigenvalue of identity. So note see this. Let's check this. Determinant of I minus lambda I. Or you can see that this is already a diagonal matrix. Eigenvalues are the diagonal entries. No need to check. So 1 is, so just check easily that 1 is the only eigenvalue of I. So 1 is the only eigenvalue of I. So 0 is not eigenvalue of I. 0 is not an eigenvalue of. So fourth option is false. Both 0 and 1 are not eigenvalue of I. Oh, let's write it here also. Not eigenvalues. So option number 4 is false. Now what is the fifth option? Idempotent matrices are always diagonalizable. Okay, so we'll prove this, that idempotent matrices are always diagonalizable. This can be proved easier, but here you do not know about the minimal polynomial or the annullity polynomial, so we will do it another way. So we will prove this. We will prove that all idempotent matrices are diagonalizable. So idempotent means a square equals to a. Given that a square equals to a, where a is the corresponding linear transformation is a map from, suppose take V to V, and where dimension of V is n. Right. So let's assume the L as dimension of the range of A is R. So let's assume dimension of the range was of A is R. R is the range space of A. So means, so there are many linearly independent vectors which span the range. So let's take u1, u2 dot ur be a basis of R of A. So they are in the range, means it has a pre-image, which implies a vi equals to ui, right, for some vi, because ui is in the range. For some vi in V for I equals to 1 to R. Right, now you will show that this ui are the eigenvectors of A with eigenvalue 1. So this is easy. So let's check. Note that A of ui, let's compute what will be A of ui. Basically we want to prove that ui is the eigenvector. So for that we will check that A of ui, what will be the, what we will get. A of ui, A is a square, so we write A equals to a square. Means A of ui, and A of ui is V. So this is A of vi and A of vi is ui. So from there you can see that ui is an eigenvector with the eigenvalue 1. So which implies ui's are the eigenvector of A with eigenvalues 1, right? So we have assumed that dimension of the range space is R. So by rank nullity, dimension of the null space will be n minus R. So by rank nullity, dimension of the null space n of A is n minus R. Right? N is the null space of A. Right. So means there are n minus R vectors which are in the kernel. Null space means they will map it to 0. So which implies n minus R vectors are in the kernel of A. So let's take this, let's take u of A of uj equals to 0 times uj, because this is 0, for taking j equals to r plus 1 2 dot 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 n minus r. So which imply uj are again eigenvectors of A with eigenvalue 0, right? So this is 0, which will it is 0 times uj, which implies uj are eigenvectors of A with eigenvalue 0 for j equals to r plus 1 to n minus r. So we got n number of eigenvectors, right? And as we can write B equals to range plus nullity in a direct sum, as B equals to range of A plus direct sum nullity of A, and where Ra as the basis, Ra is the span of u1 dot 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 ur, and n of A is the span of ur plus 1 dot 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 un minus r, and both are all of them are eigenvectors. So which implies B as a basis consisting of eigenvectors of A, which implies B as a basis consisting of eigenvectors of A, which imply A is diagonalizable. So we start with the assumption that A is idempotent and prove that A is diagonalizable. So the option number 5 is correct. All the idempotent matrices are diagonalizable. Question number 1 is done. Let's move to question number 2. We have 4 matrices are given. You have to check which of the following matrices are diagonalizable over R. So for that you have to find the characteristic polynomial and the eigenvalues. So let's check the first one. Let's call it A1 1 0 1 0 1 0 1 0 1. So compute the determinant of a1 minus lambda I equals to 0. So what will be the characteristic polynomial? I just write it down. So determinant of 1 minus lambda 0 1 0 1 minus lambda 0 1 0 1 minus lambda equals to 0. So if you compute the determinant, you will get 1 minus lambda cube minus 1 minus lambda equals to 0. So if you solve this, what you will get? You will get lambda 1 minus lambda into lambda minus 2 is 0. So A has the eigenvalue 0, 1 and 2. 0, 1 and 2. So A is a 3 cross 3 matrix. You get 3 distinct eigenvalues, which implies A is diagonalizable, as A has 3 distinct eigenvalues. Imply A is diagonalizable. So option number 1 is correct. First matrix is diagonalizable. Let's check the next one. 2 1 0 1. So this is A1 and this is A2. A2 is 2 1 0 1. So this is upper triangular matrix. So it has the eigenvalues 2 and 1, which are in the diagonal entries, right? So this you can also easily calculate. Determinant of A2 minus lambda I equals to 0, which implies determinant of 2 minus lambda 1 minus lambda is 0, which will get 2 minus lambda 1 minus lambda is 0, means lambda equals to 1 and 2. So here also the eigenvalues are distinct, which implies A is diagonal, A2 is diagonalizable. So the option number 2 is correct. Now check the option number 3. 1 1 1 1 1 0 minus 1 1 0 0 0 2. One one zero minus 1 1 0 0 0 2. So let's compute the characteristic polynomial of A3. Determinant of A3 minus lambda I equals to 0. So it will be 1 minus lambda 1 0 minus 1 1 minus lambda 0 0 0 2 minus lambda is 0. Okay, so if you compute this, the determinant of this matrix, what you will get? You will get 1 minus lambda squared, 2 minus lambda, so basically into 2 plus 2 minus lambda equals to 0. So if you simplify this, what you will get? 2 minus lambda into lambda square minus 2 lambda plus 2. So you get a quadratic polynomial here. So what are the roots of this? You can check that this has imaginary roots, means it does not have all three are real roots. So what is lambdas? Lambda will get 2 and other will be, so if you apply, so it is minus b means 2 plus minus square root of b square minus 4ac is 8 by 2. So this is imaginary number, 2 plus minus 2y. So it do not have real roots, which imply A is not diagonalizable, as A has only one eigenvalue only one real eigenvalue. And two imaginary eigenvalue. Which imply A is not diagonalizable. So option number 3 is false. A is not diagonalizable. Now let's check the last option. It's a 4 cross 4 matrix. But this is easy, you can check that this is a upper triangular matrix. So then what will be the eigenvalues? So it's the diagonal entries. And all the diagonal entries are distinct. So it will be diagonalizable. Right? So this is option number 4. A4. So what is A4? 1 0 2 3 0 0 2 3 0 0 2 3 0 0 0 3. So note that A4 is upper triangular matrix. So the eigenvalues are just the diagonal entries. Are just the diagonal entries. So lambda equals to 0, 1, 2, 3 are the eigenvalues of A4. And as all are distinct, as all the eigenvalues are distinct, which imply A4 is diagonalizable. Right, so option number 4 is again correct. A4 is diagonalizable. Okay, so question number 2 is done. Let's move to question number 3. A matrix 3 2 1 4, a 2 cross 2 matrix is given. Then we have to check which of the following statements are true for matrix A. First option is characteristic polynomial is given. You have to check that this is correct or not. So A is 3 2 1 4. So what will be that? So we are doing option number 1. What is the characteristic polynomial? So you have to compute the determinant of A minus lambda I, right? So this is the characteristic polynomial. Goes to this. So determinant of 3 minus lambda 2 1 4 minus lambda. So what is the determinant? 3 minus lambda 4 minus lambda minus 2 equals to minus 2. So if you simplify this, you will get lambda square minus 7, lambda square minus 7 lambda plus 10. So this can be written as lambda minus 5 into lambda minus 2. So the first option is correct. What it is written is correct, means characteristic polynomial is lambda minus 2 into lambda minus 5. A is diagonalizable. Next option 2. So what are the eigenvalues? Determinant of A minus lambda is 0. So from here you can see that lambda minus 5 into lambda minus 2. So roots of the characteristic polynomial, lambda is 2 and 5 are the eigenvalues of A. Which are distinct, means A is diagonalizable. Imply A is diagonalizable. Right, because the eigenvalues are distinct, so option number 2 is correct. The option number 3 is saying that there is an invertible matrix Q such that Q inverse AQ is 2 0 0 5. Right. So this is just the definition of diagonalizable. So if you write down, because we have seen that A is eigenvalue 2 and 5, so A is diagonalizable means, so we can, as A is diagonalizable, which implies there exists invertible matrix, Q such that A will be Q D Q inverse, or D will be D is the diagonal matrix consisting of eigenvalues, right? 2 0 0 5. So now as Q is invertible, so you can multiply both by Q and Q inverse, so you get Q inverse A Q equals to D, which is the 2 0 0 5. So which is the option number 3. So option number 3 is correct. Now you have to check the option number 4. Option number 4 is saying that there is invertible matrix Q, say that Q inverse AQ is 3 0 0 2. So this is option number 4. So can this happen that A can be written as diagonal matrix with entries 3 0 0 2, 3 and 2. So if this will happen, then 3 will be eigenvalue, right? But this is not so. So there will not exist any invertible matrix, right? So we'll prove this. So suppose if there exists an invertible matrix Q such that Q inverse AQ is 3 0 0 2, which you denote it by D, means A is diagonalizable, which is same as A Q D Q inverse, or D is this, right? And so A can be written as, which implies lambda equals to 2 and 3 are the eigenvalues of A. Which is a contradiction, right? Which is a contradiction to what 3 is not an eigenvalue. Contradiction to the fact that 3 is not an eigenvalue of A. So option number 4 is false. That does not exist in invertible matrix which will satisfy this. Now what is option number 5? There is an invertible matrix Q such that Q inverse AQ is 5002. So this has basically changed the entries. 2005, it's 5002. So if you change the basis of Q, means if V1 in terms of basis, if you write Q1 is the V1 V2, if you take V2 V1, the eigenvalue will flip. So there exists an invertible matrix and the Q will remain invertible. So let's check option number 5. So we have early we have what we have. So as we have, or as we know, two and 5 are the eigenvalues of A. Let's say let eigenvalue corresponding to 2 is V1, let A V1 equals to 2 V1 and A V2 equals to 5 V2. So if you take Q2 with this matrix V1 and V2 column wise, then with this basis A can be written as, take Q2 with this, then A can be written as A equals to, it will be Q D Q inverse, where D is this 2005. Now flip this basis, so this I am taking Q1, now take Q2 V2 comma V1. So just we are changing the order of the basis, it will remain invertible. Then A can be written as A will be Q D Q inverse, where D the diagonal entries will flip. So 5 will here 5002, right? So which means Q inverse A Q is D, which is 5002. So option number 5 is correct. There indeed exists an invertible matrix Q, or such that Q inverse AQ is this. So with this question number 3 is also done. Now let's move to question number 4. What it is saying, T be an linear operator on a finite dimensional vector space B, and suppose lambda is an eigenvalue of T with eigenspace E lambda, then you have to check which of the following statements are true. So what is E lambda? E lambda is the corresponding eigenspace with eigenvalue lambda. So E lambda consists of all this B such that T V equals to lambda V. So this is a linear space. You have to check that if W is an T invariant subspace of B, then it is T to the power n invariant subspace of B for all n. So what is invariant subspace? So it's saying that, so let's given that W is a T invariant subspace. So what is meant by T invariant subspace of B? So which means if some vector, suppose W is in W, capital W, if we apply the T over W, then it will remain in W, right? And W, so then we call that W is the T invariant subspace of B. So you have to check here, if W is the T invariant subspace, then T to the power n, it is also T to the power n invariant, right? So let's check. Then T to the power n of, let's take W from, then what will happen? T to the power n minus 1 composition T of W, right? And you know for W is in W, you have to start with. So T of W is in W, so T of T to the power n minus 1. So this is V, or you know V is in W, right? As TW is in W, right? So if you do another step, you will get that this will belongs to W, right? So you have shown that if W is T invariant, then W is also T to the power n invariant, which implies W is T to the power n invariant. So the first option is correct. W is T to the power n invariant subspace for all n. Now let's take option number 2. The 0 subspace and V, the whole subspace, vector space, are always T invariant subspace of V. So these are just by the definition of linear operator. So we know that T is a map from V to V, and this is linear, right? And T is linear. So linear means T map 0 to 0, 0 element to 0 element, right? So which implies 0 is the invariant subspace, which implies 0 subspace is invariant under T. Zero subspace is invariant under T, and T is a linear operator from B to B, so it's trivially it's really invariant. B is in invariant subspace of T. As the map from B to B, which implies B is also invariant under T. So option number 2 is easy, it's done. Now check the option number 3. If W is an T invariant subspace of V, then it is CT invariant subspace of V, right? So now the you have to check it is invariant under CT. So option number 3, what it is given that W is T invariant subspace. You have to check it is CT invariant subspace for all C now. So we have to show, we will show W is CT invariant for all C in real number, right? So let's take B. B is in W, one element from W. Let's take B from W, then apply CT to B. So what will it become? CT of B, and as W is T invariant, so TV is in W, and this is a subspace, so this is in W. Why? As W is in subspace, as W is a subspace, and T invariant. Right, TV is in W and C times TV will also be in W because it's a subspace. Right, so this is what you have to show. So which implies W is CT invariant. So option number 3 is also correct. Now come to the option number 4. E lambda is PT invariant subspace of B for any polynomial P. So what is E lambda? E lambda is the corresponding eigenspace. So you have to check that this E lambda is invariant under any polynomial of T. So this is option number 4. So what is E lambda? E lambda is all such B in B such that TV equals to lambda V. And what is PT? So suppose what is definition of P of T? Take any polynomial. So let P of x to be a naught plus a1x plus dot dot an x to the power n. Then what will be the PT? PT will be simply a naught times identity plus a1 a plus dot 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 n a to the power n. So this is the polynomial in of T. Sorry, I have written it in a1 T. So this is the polynomial in T. You have to check that E lambda is an invariant under this polynomial, right? So what will be PT? Suppose you have take V, or V is in from E lambda. So what is PT? A naught I plus A1 T plus dot 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 A n T to the power n B. And you know one fact that V is an eigenvector of T with eigenvalue lambda. So it will be a naught V plus a1, it's TV plus a2, it will be T square V, right? Dot 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 an T to the power n B. So if V is an eigenvalue of T with eigenvalue lambda, then V is an eigenvalue of T square with eigenvalue lambda square, or more generally T to the power n with eigenvalue lambda to the power n. So we will use this. So it will be a naught V plus a1 lambda V plus a2 lambda square V plus dot 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 n lambda to the power n V, right? So what we've got? A naught plus a1 lambda plus a2 lambda square plus dot 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 an lambda to the power n V. So what you have said, this is exactly the polynomial when you substitute the value of lambda. So this is P lambda of B. So what we have shown that PT of B will be P lambda of B, right? Now P lambda is basically a complex number or a real number or complex number, whatever. So here it's real number because this is a real valued polynomial. So PT of B equals to P lambda of B, where P lambda is real number and E lambda is a subspace, right? Because these are eigenspace as E lambda are eigenspace. So P lambda of B also is in A lambda, which implies PT of B is also in A lambda. Means E lambda is PT invariant. E lambda is PT invariant subspace. So option number 4 is correct. E lambda is pt some invariant subspace of V for any polynomial P. Now let's check the last option. If T has exactly n minus n distinct eigenvalues lambda k, then E lambda I intersection E lambda j is non-empty for some I less than j. So it's saying that corresponding to different eigenvalues, their eigenspace can intersect. But this is not true, right? We have seen in the class. So let's do this. Let E lambda I and E lambda j are the corresponding eigenspace of lambda I and lambda j. Suppose let's they intersect. Suppose E lambda I intersection E lambda j is non-empty. So let's take an element B. Let B is in the intersection. So E is in both where I not equals to j for two distinct eigenvalues. So which implies B is in E lambda 1 means Tb equals to lambda I B and Tb equals to lambda JB, right? So if you subtract these two, which implies lambda I minus lambda j of B equals to 0. But I not equals to j means lambda I not equals to lambda j. So this is imply B should be 0, right? So the only element which is in the intersection is 0. So they are disjoint, which implies E lambda intersection E lambda j trivial means disjoint for I not equals to j. So option number 5 is false. They cannot intersect that for disjoint eigenvalues, the eigenspace. So question number 4 is done. Let's move to question number 5. It's saying that T be a linear operator on a given vector space B and W be a subspace of B, then which of the following subspace is T invariant subspace of B? We check which of the following are T invariant subspace. First option, B is in R2 and T is an operator which is mapped from R2 to R2. T of x1 x2 it will map x1 plus x2 comma x1 plus x2. And what is the subspace? W is given. W is T comma T such that T is in R. We check that this W is T invariant subspace or not. So let's take an element and apply T. Then T of T apply with this. Then where it will map T of T plus T, it's 2T comma 2T. So it will be 2 times, sorry. So it will be 2 times T comma T, right? So T comma T are basically, so this is 2 times and W is a subspace, means this is again in W. So W is a T invariant subspace of T. W is a T invariant subspace. Option number 1 is correct. Let's what is option number 2? B is the set of all polynomials over R. T of fx is x times fx, and W is polynomial of degree n. So let's check this. So B is P of R. This is set of all polynomials of degree of set of all polynomials with coefficients in R. And what is T? T is mapped from P of R to P of R. T of fx is x times fx. Then is what is W? I have taken Pn of R. This is polynomial of degree n. So let's take simply x to the power n and apply T. Take x to the power n, which is in W, Pn of R, polynomial of degree n. Then if we apply T of x to the power n, it will simply be x into x to the power n, which is x to the power n plus 1, which belongs to P of n plus 1. So which implies W is not T invariant subspace of P. W is not T invariant subspace of B. So option number 2 is false. Option number 3, it's again the same space. B is the set of all polynomials, and then now this time operator is x times f dash x, and here the space is Pn. So let's check. B is P of R, and T is from P of R to P of R. T of fx, this is x times f dash x. So we'll show that okay, let W is PNR. So what is the general polynomial? Means we will show that W is invariant subspace of T. So you have to take a general polynomial and apply T. You have to show that it is again land in W. So take Px a0 plus a1x plus dot 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 an x to the power n. This is in W. Apply T of Px. So to x into P dash x, right? What is P dash x? It is a1 plus a2 2a2x plus dot dot an x to the power n minus 1. So you multiply by x, then it is again a n degree polynomial. a1x 2a2x x square plus dot 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 an x to the power n. So which is in W. So which means W is in T invariant subspace. Of B. So option number 3 is also correct. Now let's check the option number 4. Now this time V is M2R, 2 cross 2 matrices. TA is 0 1 1 0 times A, and W is the antisymmetric matrices, set of all subspace of antisymmetric matrices. So this is option number 4. B is M2R. T of A is 0, 1, 1, 0. Times A. W is the A belongs to B, such that A transpose equals to minus A. So you have to check the W is T invariant or not. So this will not be T invariant subspace. So let's take this A. Take A to be 0, 1, minus 1, 0. Then if you transpose it, you can check that A transpose is minus A. Means A is antisymmetric. This you can check. Now apply T to A. So what will happen? 0, 1, 1, 0. 0, 1, minus 1, 0. So what will get? Minus 1, 0, 0, 1. But this does not belong to W, right? Because this is not a skew symmetric matrix, which implies W is not T invariant subspace of B. So option number 4 is false. Oh, sorry, this is false. Now check the option number 5. This is MNR matrix and TA is A transpose, and the subspace is all trace zero matrices. B. So question number 5, B is MNR. T of A is A transpose, and W is all A in B. So the trace of A is 0. So what is the trace of a matrix? It is the sum of diagonal entries. So if you just write down a general matrix A in terms of Aij, n cross n matrix A1 1 dot 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 A1 n AN1 dot dot ANN, then trace of A will be sum of AII, right? All AII, all these are same, means diagonal entries. I equals to 1 to n. Now if you transpose this, then the diagonal entries remain same, right? What will be a transpose? A transpose will be, so row you have to write in terms of column A11 A1n dot 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 AN1 dot 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 ANN, but the diagonal entries will not change, right? They will be same. Then trace of A transpose is also the summation I equals to 1 to n AII. Right. So if you apply the transpose, then the diagonal entry is not changed, means the sum of diagonal entry is not changed, so the trace will not change. So 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 if A is in W, which implies T of A, which is A transpose, which is also in W, right? Means W is in T invariant subspace of B. So option number 5 is true. Oh, sorry, what is, so W is trace a 0, so means all trace remains same. So if trace is 0 of A, then trace of A transpose is also 0. Right. So trace of A transpose and sum of AI again, I equals to 1 to n, and this is again 0, which implies T of A is in W. W is T invariant subspace of B. So option number 5 is correct. So this completes the assignment, question number 5. Now let's move to the last question, question number 6. Which of the following statements are true? You have to check. First option, it's done in the class. If T has distinct eigenvalues, then T is diagonalizable, right? So T is a map from B to B, where the dimension of B is n. If T has n distinct eigenvalues, then the corresponding, so let me write it down. So let T be a linear operator from B to B, where dimension of B is n. If T has n distinct eigenvalues, which implies the corresponding, so which implies T has n distinct eigenvectors and which are linearly independent. T has n many linearly independent eigenvectors, so they will form a basis. So B has a basis consisting of eigenvectors. B has a basis consisting of eigenvectors of 2, T consisting of which means T is diagonalizable. Option number 1 is true. Now check the next option. The characteristic polynomial of any diagonalizable operator, linear operator, splits. So what does it mean that characteristic polynomial splits? Let's write down it. Splits mean the polynomial can be written down a factor of linear factors. So a polynomial splits over R. It's saying that splits over R or something. Here means not mention, means over real number. Splits over R. Let me write. means it can be factored into linear factors. What are linear factors? Means degree 1 polynomial, right? So polynomial splits means it can be written as product of linear polynomial. So it's saying that the characteristic polynomial of any diagonalizable linear operator splits. So we'll prove this. If T is diagonalizable, then its characteristic polynomial splits. So this is the definition. So that the characteristic polynomial of linear operator of any diagonalizable operator. Diagonalizable linear operator splits. So first take T is diagonal matrix, then what will happen? First take this. So prove. So if T is diagonal matrix, then what will happen? Means T can be written as, so suppose this is n1, lambda 1, lambda 2, dot lambda n, and all other entries are 0, right? Then what will be the characteristic polynomial? Then characteristic polynomial p lambda, this you can compute, it will be lambda minus lambda 1 dot lambda minus lambda n, right? So from here you can see that this is the product of linear factors, which implies the characteristic polynomial splits. Okay, so this is case 1 when T is diagonal matrix. Now what happened? T is diagonalizable, not diagonal matrix. So this is case 2. Let T is diagonalizable matrix. Diagonalizable matrix. So what is diagonalizable matrix? Means then T can be written as, which implies there exists invertible matrix Q such that T can be written as Q D Q inverse, right? Where D is diagonal, Q is invertible. Then what will be the characteristic polynomial of T? Then if you compute T minus lambda I, then it will be Q D Q inverse minus Q lambda I Q inverse. So this is basically Q d minus lambda I q inverse. Now if you take the determinant of d minus lambda I, so it will be determinant of q, because determinant of AB is determinant of A into determinant of B. We will use this d minus lambda I, and determinant of A inverse of det q inverse, and this will cancel, so it is simply determinant of d minus lambda I. So the characteristic polynomial of T is same as characteristic polynomial of D, and now, but D is diagonal matrix, so characteristic polynomial of D will splits. So characteristic polynomial of T is same as polynomial of D, but D is a diagonal matrix. So for D we know that characteristic polynomial splits, so which implies the characteristic polynomial of T also splits. Polynomial of D splits, so this is by case 1, so which implies characteristic polynomial of T is also splits. So this completes the proof that characteristic polynomial of any diagonalizable linear operator splits. So option number 2 is correct. Now what is option number 3? If the characteristic polynomial of linear operator splits, then T is diagonalizable. So this is the converse of the above statement. It is saying that if the characteristic polynomial of linear operator splits, then is T diagonalizable or not? So we'll show that this the converse of the above statement is not true, means the option number 3 is not true. So this is option number 3. So it might happen the characteristic polynomial splits, but T is not diagonalizable. So if the characteristic polynomial of what is of T splits, then T may not be diagonalizable. So let's take the first example what we have done at the very beginning of the today's tutorial. What you have taken, so let's take the same example, T to be 0 1 1 0 0 0. So this we have taken the first example of the first question. There we have shown that T is not diagonalizable, right? So what we have shown there in the option question 1, we have taken T to be A to be this, and we have computed the characteristic polynomial which is lambda square. So this is the product of lambda into lambda, which are linear factors, right? So means characteristic polynomial splits, and we have also shown T is diagonalizable. So as done in question 1, the characteristic polynomial of t is p of lambda, which is lambda square. So which is lambda into lambda. So which implies characteristic polynomial characteristic polynomial of t splits. But we have shown in there, but we have shown that t is not diagonalizable. That t is diagonalizable. T is not diagonalizable, right? So the option number 3 is false. Characteristic polynomial might splits, but t may not be diagonalizable. So option number 3 is false. Now what is option number 4? This is a big option. Let t be a linear operator on finite dimensional vector space B such that the characteristic polynomial of t splits and lambda 1, lambda 2 up to lambda k be the distinct eigenvalues of t. Then t is diagonalizable if and only if the multiplicity of lambda is equal to the dimension of the eigenspace E lambda for all I. Okay, it's saying that diagonalizable if and only if the multiplicity of eigenvalues the same as the eigenspace, dimension of the eigenspace. So this is true. We will prove this. This is option number 4. What is this linear operator? On a finite dimensional vector space B such that the characteristic polynomial splits let lambda 1 up to lambda k be the distinct eigenvalues. Then t is diagonalizable if and only the multiplicity of lambda I lambda is equal to the dimension of the eigenspace E lambda I, right? So let's prove this. So first prove the forward direction. Let's assume t is diagonalizable. So means there exists a basis in which t can be written as diagonal matrix. So by interchanging the basis we can write it, which implies there exists a basis such that the corresponding matrix of t with some basis, suppose say beta, you can write it as lambda 1 I n1 with multiplicity, suppose say n1 for the lambda 1, lambda 2 I n2 dot 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 lambda n lambda k I n k, right, and all other are 0. This we have done by reordering the basis. This can be done by reordering. Just take the same eigenvalues and club them and write in this form. Reordering the basis with equal eigenvalues. So then what will be the characteristic polynomial? Then characteristic polynomial of t will be so let's call it p lambda. It will be lambda pt or lambda minus lambda 1 to the power n1 dot 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 lambda minus lambda k to the power nk, right, or minus 1 to the power something can happen n, where ni are the dimension of the dimension of e lambda I. So this we have to prove that if t is diagonalizable, then the multiplicity, so this is the number of times the lambda is repeating lambda is, these are the multiplicity, right, n1 n2, and so this will be the dimension of the eigenspace corresponding to lambda I. So if t is diagonalizable, we have proved this. Now we have to prove the converse. So suppose let characteristic of polynomial of t splits, and it will look like this. Polynomial of t is, suppose say lambda 1 minus t to the power n1 dot 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 lambda k minus t to the power nk, with ni is the dimension of e lambda I. Then we have to prove that t is diagonalizable. So corresponding to different distinct, and also lambdas are distinct, we know. Also we know lambda 1 up to lambda k all are distinct. So take the basis, suppose beta I are the basis for e lambda I. Then if you take the union of all the bases of different e lambda, then it will be a linearly independent set. This was done in the class, and this will form the basis of B. So let beta I be a basis of e lambda I. Then by the theorem done in the class, beta, which is the beta 1 union dot 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 beta k, is linearly independent, right? this set beta, which is the union of all the basis elements corresponding to different lambdas, this set will be linearly independent. And what will be the number of elements in beta? So if you take the cardinality of beta, it will be beta 1 has a cardinality of n1 plus dot 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 nk, right? So beta has cardinality n1 plus up to nk. And also note that this is the characteristic polynomial, so it has a degree or dimension of the space. So also note degree of, suppose let's call it pt, characteristic polynomial, so it has degree dimension of the polynomial a space. So note degree of pt is equals to n1 plus dot 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 nk, which is the dimension of the space V, right? Because this is a characteristic polynomial, as pt is characteristic polynomial. Right. So therefore, so these two are same. So we get the cardinality of beta is the dimension of B. So beta is also the linearly independent set, and it has the cardinality dimension of B. Means beta is a basis of B, which implies beta is a basis of B. So what we have then got, that B has a basis consisting of eigenvectors. B has a basis consisting of eigenvectors of T, right, which implies T is diagonalizable. So this proves the other direction. So option number 4, we have proved it. So this is correct. Now let's check the last option. Let T be linear operator on finite dimensional vector space such that the characteristic polynomial of T splits. For each eigenvalue lambda of T, the multiplicity of lambda equals to n minus rank of T minus lambda. So it's given that characteristic polynomial T splits. Then you have to check that what will be the multiplicity of eigenvalue. Is it n minus rank of Ti or not, lambda I or not? This is option number 5. What it is given, given that the characteristic polynomial T splits now we have to compute the multiplicity of lambda I. So let lambda be an eigenvalue of T. Then what will be E lambda? E lambda, this is basically the eigenspace of, so E lambda is all such B such that Tv equals to lambda V, means all such B such that T minus lambda I into B equals to 0. So this is the null space of T minus lambda I, right, because T minus lambda I into B equals 0. So this is the null space of T minus lambda. So nullity of T is the dimension of EI, right? Therefore nullity of t minus lambda I is the dimension of E lambda. So by rank nullity theorem, dimension of E lambda, you can also write n minus the rank of t minus lambda I. So what we have seen here, the dimension of E lambda is the n minus rank of t minus lambda I. Now we will show that this may not be equal to always equal, right? So let's check. So let's take the same example as we have taken earlier, the past tense subtle, or this as in the first example. Take T to be this matrix 0 1 0 0. Then we have seen the characteristic polynomial, then characteristic polynomial of t is given by this we have computed earlier, is lambda is given by lambda square, right, which imply characteristic polynomial splits. And also we have computed the and lambda equals to 0 is the only eigenvalue, of t, and we have also computed the eigenspace E0 is the all such v such that tv equals to 0 v. This we have computed, we have shown earlier that this is x comma 0 such that x is in R, right, as shown in the first question. So dimension of E0 is 1, right? But what is the multiplicity of lambda? It's a 2 because lambda square. So note that dimension of E0 is 1. So by star dimension n minus rank of lambda is 1. By star n minus rank of t minus lambda I is 1, right? But note that for a multiplicity of lambda equals to 0 is 2, right, as lambda square equals to 0, right, as determinant of a minus lambda equals to 0 imply lambda square equals to 0. So this is not true, multiplicity of lambda is not equals to, so therefore multiplicity of lambda is not equals to the n minus rank of t minus lambda. So the option number 5 is false. So the last option is false. So this completes the question 6 and also the assignment 8. Okay, so the assignment 8 is done. So let's stop for today. Let me stop the recording.